Hi, welcome back to Statics 1. Today we're going to move on to a new subject, which is to talk about moment force. A moment is essentially a rotational force. It's a force that causes an object to rotate. It's kind of a circular, no pun intended, definition of what a moment is, but I wanted to give you kind of an example. Back in the day when I used to work on engines, we had what was called a torque wrench, and I'll just draw kind of a cartoony picture of what a torque wrench looks like. And okay, so here's my wrench. Essentially, you can imagine, here's the handle of the wrench, and here's the part where it goes on the nut. And I'll just draw kind of a cartoony image, and then there would be a nut over here. And you can imagine that we apply a force to a wrench, and then on the torque wrench there was actually like a little needle here. There's a scale here, and there's a needle, and as you turn this thing, the more force you applied here, the more this needle would move on the scale, and it would actually measure how tightly you would tighten the nut. It was important because you have like specs particularly for certain nuts that you don't want to have them too loose that things vibrate off, but you also don't want to make them so tight that you can break the bolt, which is possible. So this is called a torque wrench, and essentially a torque wrench. And torque is essentially encapsulates what a moment is. It's something that's causing. It's the measurement of that rotational force. And I think you could probably intuitively understand, or maybe based on like your background in physics, that if we made this torque wrench twice as long, and then instead of applying the force here, I applied the same force here, I think you'd realize that the torque that occurs at this end is going to be larger. You're actually getting more force out of this thing down here at this end, the more rotational force, a higher torque or a higher moment. So in fact, the torque that's applied at that point, the moment that's applied, equals the force times what we call the perpendicular distance. So what you want to do in this case is draw a line perpendicular. You have your line of action of your force, and we're going to draw a line perpendicular to that, to the point where we're evaluating the moment. And so I'm going to take that distance, d, that's my perpendicular distance, and the moment equals the force times that perpendicular distance. So this is the perpendicular distance. And this is a source of constant confusion to people, and I'll show you why. In this case, it's kind of obvious, because here you have your wrench, and obviously we're applying a force. Hopefully this is, well, almost perpendicular. The force is being perpendicular to the length, the shaft of the wrench, and it's kind of obvious what that perpendicular distance is. Anyways, let me write here that the moment, or it's actually the magnitude of the moment. So in fact, a moment is a vector quantity, and because it has a direction and it has a magnitude. So the magnitude of our moment, which I'll just call m naught, because we have here 0.0, so it means that's the moment about 0.0 equals the force times the distance, times the perpendicular distance. Perpendicular distance. All right, now I'm going to show you another case where it's not really obvious what that perpendicular distance might be. Imagine that I'm going to erase this F here. I'm going to put a new force in here. And it's not going to be perpendicular. It's not going to be applied perpendicular to this shaft, but it's applied at some angle. Like, let's say this. So here's my force. It's essentially a force vector, but it's not applied perpendicular to the shaft. In fact, there's some angle here, theta. Now, if you look at this thing, what is the perpendicular distance from this force to the point where you're evaluating the moment? And how do you find that? Okay, what we do is we find the line of action of our force, which is just a line parallel to our force. And I'll just continue it off both directions. Here it is in green. This is called the line of action. Okay, so where do we evaluate the perpendicular distance? We find the line here that's going to make a perpendicular. We're going to find a perpendicular line to our line of action that intersects the point where we're evaluating the moment. So I'm going to draw a line vertically, hopefully, almost vertically upward. Not bad. Anyways, I think you get the point. This is perpendicular. That's my new perpendicular distance, d. So in this case, the moment applied here equals the force times that distance. And as you can see, it's much less than the total distance of the shaft. And that's because the force is not being applied, what you might say, optimally perpendicular to that shaft. All right, so what would that value d be in relation to, well, the length of that shaft? Well, if we call that shaft r, or we call this shaft length r, then we have, basically we have a right triangle here, right? With theta here. The side opposite is our d value. That's that perpendicular distance. And this value will be equal to r times sine theta, because we have opposite over hypotenuse. That will give you, if you multiply the hypotenuse times opposite of hypotenuse, you end up with the opposite value. So in fact, in a more general case, the moment equals F times R times sine theta. And this F is obviously the magnitude of the force F. This R is the length of the distance between the point where the force is being applied and the point where we're evaluating the force. And the theta value is the angle that's made between that force and this line here, where the wrench is. Okay, so in general, we can say, and I'm going to write here F times D, okay, where D is the perpendicular distance, which equals that R sine theta. Okay, so hopefully this kind of gives you a good introduction to moments. There's actually one more point I wanted to make, which is, now in this case, everything is in the plane of the board, right? The force is in the plane of the board. Our wrench is in the plane of the board. So the moment is, and as I mentioned before, it's a vector, but the moment in this case will be coming directly out of the board. So if this was x, y coordinates, our moment would be coming out of the board in the z direction. So you would actually write the moment that's created by pushing on this wrench is going to be equal to m. And this time it's a vector, m naught with an arrow on it. It's a vector equals f r sine theta, no surprise, times k, our unit vector. Okay, and the principle is, so it's out of the board, k, there's no, the k basically defines, it's perpendicular to the plane that's formed by this shaft and the force. So in this case, that the vector is perpendicular to this xy plane. And you might wonder, well, why is it not into the board or out of the board? How do we decide if it's into the board, in other words, a negative k value, or out of the board, a positive k value, in the direction of z, which this one would be in the direction z? By the convention that we're going to use is that if you have a counterclockwise rotation, which in fact this is, right? Because this is pushing it this way. We're holding this here. We're pushing this up in this direction. So it's like we're going from 3, 2, 1, 12, right? Counterclockwise. That's going to be defined as a positive moment vector. And it's exactly what we do when you took trigonometry and someone showed you the unit circle. We had a unit circle. Sorry. And you had a point here, and you had some angle theta. You remember how we defined theta, and we were talking about cos theta and sine theta? It's the same thing. A counterclockwise is interpreted as a positive vector. So it's going to have a positive value. If this had been going in the other direction, then the value of k would be a negative value. We'd have, in other words, I would write it as negative FR sine theta times k. And in that case, it would be going into the board, because x, y, and z in this case comes out of the board. All right, so just don't forget this, that a moment is a vector, and a counterclockwise rotation is positive. Okay, counterclockwise, CCW, rotation is positive, greater than 0. Okay, so it's a really important point. And it's something that's constantly people get confused about. So if you can get it right from the get-go, then you should be okay. All right, I think I've covered it. Okay, I've covered everything I wanted to about moments. The next thing we're going to talk about is a cross product, which is a great way of determining these moments, particularly when we get into, like in 2D, no problem. You can just use FR sine theta. But when we get into 3D rotation, it's much easier to use the vector formulation, and we're going to use the vector cross product of a vector that describes the force and this shaft r, or the distance between the point where the force is applied and the point where the moment is being evaluated. So those are the next topics that we're going to be talking about. So if you have questions about this, send me an email and I will see you in class.